Swayam Prabha. Digital India. Educated India.
Students, we meet again today for the second lecture on consolidation and settlement. As is the practice, I will briefly review what we have already gone through in the previous lecture. Furthermore, this topic is of so much practical importance. This affects every building that is built on soft soil. And you know, such buildings are many on waterfront in particular, where you find marine or riverine clay deposits. In view of this importance of this topic, it is absolutely necessary that the very basic fundamentals regarding consolidation behavior of a clay is well understood. Therefore, I will go over some of these basic concepts once again. Let us take a look at the slides to begin with. In the last lecture, we gained a fundamental idea about the consolidation phenomenon. That is, what is this phenomenon all about? What does it consist of? How does it take place? And we also saw towards the end of the lecture how to compute the effect of this consolidation behavior, that is, how to compute the amount of settlement that a building will undergo. So, we started with answering some basic questions. Essentially, we answered 2 questions out of 5 which I had raised, which I had posed. The 2 basic questions I had raised were, what is consolidation and what is settlement? Until we really understand what is consolidation or what is settlement, it is very difficult to understand their relative importance, understand where it is really important, and also to know how to make reliable computations about the effect of consolidation in any given situation. So, what is consolidation? There are many different ways in which we can probably explain this. Let us see what causes consolidation once again briefly, and then come to the formal definition of consolidation. Let us take a look at the next slide. What is consolidation? It is a form of stress strain behavior. That is, you apply a stress, there is going to be a strain. So, consolidation is all about application of a load and the resulting deformation, or application of a stress and the resulting strain. So, stress strain behavior results in consolidation. Now, it is obvious that different soils, even clays themselves, will have different stress strain relationships. Also, although the basic pattern may be the same, the actual stress strain relationship could be different from clay to clay, and therefore, the degree to which consolidation will take place under a given load will vary from place to place, and it is required therefore to have a unified theory which will explain to us for a given stress how we can possibly evaluate what strain will result. So, what is consolidation? Once again, it is nothing but stress strain behavior. And what is settlement? It is a form of compression. When a stress is applied, when strain takes place or when deformation takes place, there is going to be a compression of the soil under the acting load, and this compression is what is known as settlement. Settlement is a result of consolidation. As I had mentioned in the last lecture, Terzaghi had pointed out there are basically two different classes of problems in soil mechanics. Those which can be considered as stress strain deformation problems and those which can be considered as stability problems. For example, if you take the stress distribution problem, which we had dealt with in some detail in one of my previous set of lectures, is a typical elastic stress strain behavior. This elastic stress strain behavior indicates that the strains are recoverable when the stress is removed, and essentially the equilibrium or the stability is not disturbed. The equilibrium in fact was ensured when we talked about stress distribution by tacitly assuming that every element of soil in a medium is in equilibrium. On that basis, we derived a set of equations which told us how stress is distributed. So, stress distribution problems inherently imply that there is equilibrium, whereas on the other hand there are stress strain time relationships in which given a stress the strain goes on varying with time, or sometimes given a strain the stress goes on varying with time, and such problems where the strain may vary can be described as viscous, plastic, creep behavior and so on. Now, these are all terms which we had briefly gone through in the previous lecture. Under this class of problems where stress strain time behavior is involved, again there are two different problems, one which can be called as the consolidation problem, another the stability problem. This consolidation problem is a problem of large deformations, high, heavy or large strains, whereas slope stability or foundation stability are problems where there are again large deformations, but these deformations indicate failure of the structure. So, we have problems in which shear stresses are less than the shear strength, but displacements are large. Such problems are consolidation problems, and we have problems where shear stresses exceed their strength of the soil, and such problems are known as stability problems. So, in a nutshell, consolidation problems are problems where there is no failure, there is no question of stability, but there are large deformations and time dependent deformations. Okay, in order to understand this consolidation phenomenon, we had gone to the very basic aspect of how a soil is made of or what it consists of. We all know that an actual soil consists of a number of soil particles or solid particles within which there are voids. Now, we know that although there are solid particles and voids present inside them, sometimes they may be filled with water. For purposes of understanding stress strain behavior, it is convenient to idealize this situation and consider what is known as a 3-phase model. It is a very well known model. I am very sure you must have been already told about this in some earlier lecture by some other speaker. Let us take a look at this 3-phase model. This 3-phase model consists of solids, that is the solid particle constituting the soil. They constitute water and air, which together fill the voids which make up the voids. So, essentially there are two components, solids and voids, and within voids again there are two components, water and air, or in more general terms fluid and gas. Now, the part which encompasses solids and the voids together is known as skeleton of the soil. So, the skeleton of a soil which is nothing but the 3-phase model, consists of solids, water and air, and if the soil is saturated, that means the air is replaced by water, then there are only 2 phases, the solids and the water. Next. Now, this is fundamental to understanding compressibility of soils. This is fundamental in the sense that compressibility of a soil depends upon the compressibility of its constituents. There are 3 constituents, the solids, water and the air. Each one has its own compressibility behavior. For example, suppose a load is applied on this 3-phase model, then first let us take gas. Gas is compressible. When a pressure is applied, gas is compressible and it does compress, but if gas is not there, then we are left only with water and solids. Is water compressible? Normally, water is not a compressible fluid, it is an incompressible fluid, and therefore, if load is applied to water, it cannot deform, and the only way it can withstand the load is by movement, and that is what is, as you are going to see, responsible for the consolidation and settlement. So, water can be taken as incompressible. Then what about the solids? The solids are also relatively incompressible under the loads to which we normally subject a soil through some civil engineering activity like a dam or a building or a retaining wall or whatever. The requirement in any civil engineering actual structure is that it should not load the soil to such an extent as to cause a failure. We are not dealing with stability or failure problems, we are only dealing with problems where the strength is not exceeded and only large deformations take place. So, the stresses are all within such limits as not to cause breakage of particles, not to cause compression of particles, which means that now the water is incompressible, the solids are also incompressible within the range of loads that are applied. Then how does compression take place? And there is no gas. How does therefore compression take place? Compression can only take place if water is expelled out of the voids and the particles orient or move, shift and reorient or readjust themselves. This in fact is the phenomenon, this in fact is the action that is responsible for what is known as the consolidation phenomenon. So, if I take a look at what is written here, compression is due to first the compression of solids, but that is ruled out. Compression could be due to water and air in the voids, but if air is not there, compression of only water, which is again ruled out, which means that expulsion of water and air or only water from the voids and readjustment of particles can only be the reason for compression to occur. So, now we can say that consolidation can be formally defined. What is the formal definition? Let us read. The formal definition of consolidation is, it is a gradual process of simultaneous slow escape of water from voids and gradual compression of soil. The word slow escape and the word gradual compression are very important, because consolidation is a phenomenon where the load is applied gently, there is no impact load, and when the load is applied gently, the water takes its own time to get expelled and the particles take time to get readjusted, and so the resulting process is slow escape of water and gradual readjustment of particles or gradual compression of the soil. So, 3 aspects are there: gentle application of load, gradual flow out of water and gradual compression of soil. This gradual flow of water out of the voids is what is responsible for the time dependency of the consolidation phenomenon. As we saw in one of the earlier slides, it is a stress strain time behavior, and the time aspect comes in mainly because of the presence of incompressible water, which can take load or which can pass on the load only by moving out. And how does it move out? Now, we must remember we are considering saturated soil, and suppose we are considering clays. We all know that the permeability of clays is very low. It could be of the order of 10 raised to minus 6 centimeter per second, which is a rather low value. It could be even be lower. And with such a permeability value and with very small voids, the water has to necessarily take time to flow out of the soil. The process of flowing out is, in view of this permeability, very slow, and that takes place over periods of weeks and years, sometimes in an actual case, depending upon the load and the soil. And this is what is responsible for the time dependent deformation, which is known as consolidation. Now, another definition for consolidation is it is a gradual process involving drainage, compression and stress transfer. The meaning of the word stress transfer needs a little explanation. Suppose we have all these particles with voids in between them and water occupying these voids. When you apply load, since the water is flowing out, so it could even flow outwards like this against the load. Now, when the water flows out, the particles are readjusting themselves, and therefore, water cannot take load. Since it is not residing in its original position, since it is moving out, what really happens is the applied load ultimately gets transferred to the solid grains as the water goes out, again gradually, and as the particles come closer and closer and come into contact with each other, a distribution of the load finally takes place in the form of certain kind of stress distribution. So, that is what is known as stress transfer. More of it we will see a little later when we look at a mathematical or a physical model which explains how this stress transfer is taking place. At this point of time, it is enough to know that the gradual process of moving out of water in turn is responsible for a gradual process of stress or the applied load getting transferred to the solid particles little by little. So, these are two formal definitions of consolidation phenomenon, and I might emphasize at this stage once again that this phenomenon is important therefore only in saturated clays. In the case of sands, this compression is not time dependent, as you will also be seeing a little later, and hence the phenomenon of consolidation is important mainly only in saturated clays. Now, we have been using the word compression, compressibility, consolidation rather freely. From this definition, you would have seen that the word consolidation explains a certain kind of phenomenon, whereas the word compression explains a certain kind of resulting action or resulting effect rather from an action. Okay. Now, this was the background which we had covered in our earlier lecture. Now, we are ready to go forward. In today's lecture, we will see further how to compute the settlement. When given a load, given a soil, given certain conditions, how to compute the settlement, what is the simplest method or what is the mathematics involved in that. And we will also see the theory of consolidation. Can we possibly describe this consolidation in terms of some theory? These are mainly what we are going to see in today's lecture. By and large, there are two aspects which are important when it comes to the consolidation phenomenon and computation of settlement. The two phenomena are when a foundation rests on a soil, let us say, and stresses are applied onto the soil, what happens is it settles. When does it settle? It settles as the water goes out. The water goes out gradually. So, the settlement is also gradual, That means there is an implication of time involved in the settlement. This means that under certain load, under certain soil conditions, the settlement is going to take place as a function of time. Now, the question arises, will it take place indefinitely? How long will this settlement take place? Well, practice or experience shows that this settlement will go on taking place theoretically up to infinite time, but in practice it stabilizes after a certain amount of time, and that is the total or the final settlement corresponding to a given load, a given structure and a given soil condition. And it is possible to calculate that total settlement, that is one type of computation. But in practice, it is not the total settlement alone which is important. We also want to know how, at what rate this settlement takes place. Suppose we are in a position to compute the total settlement and we find that the total settlement is, let us say, 6 centimeters. Well, that alone is not sufficient, because we would like to know in practice, for a given building, for a given load, these 6 centimeters will take place over what period of time. It is, suppose, 10 years, then this building is going to undergo deformation for a period of over 10 years, and the settlement is very gradual, and probably the building will be able to withstand this gradual settlement, adjust to it without undergoing distress. But imagine a situation where this 6 centimeter settlement takes place, say, in 1 year. 6 centimeter settlement taking place in 1 year is rather fast, and the building may or may not be able to adjust itself to this rate of settlement. And therefore, it may be that the total settlement is within some reasonable limits which the building can tolerate, but if the rate is fast, then the building could show some distress. But a question will arise, how can the rate be fast? Now, we have just now defined consolidation as a gradual process, but now the word gradual or the word fast are relative words. Relative to the building, if the settlement rate is fast, then the building may show distress. If the building is such that a certain rate of deformation can be tolerated by it, then we will say that rate is slow. Obviously, it depends upon the rigidity of the building. Imagine a building versus an earthen embankment. In the building of this type which I have drawn here, the settlement could be relatively rapid for a building which is quite rigid. Consider, on the other hand, an embankment. Suppose I have a road embankment made of soil. This road embankment is obviously flexible. This being flexible, when it undergoes settlement and takes place, rather takes a shape as shown here, even if the settlement is relatively rapid, that is 6 centimeters in 1 year, this being a flexible structure, it can withstand that and maintain certain amount of stability without cracking or without undergoing distress. And this is what dictates the importance of knowing the rate of settlement, the rate at which settlement will take place. We are generally not very much worried about settlements that take place below a road unless they reach excessive limits, but we are certainly worried not only about the total magnitude of settlement undergone by a building, but also the rate of settlement. Therefore, depending upon the structure, the total settlement is really of course important, but the rate of settlement might also be important in structures where the adjustment is not easy. In order to compute this settlement, both the total magnitude and the rate of settlement, we will make a simplifying assumption. I made a brief reference to it in my last lecture. The assumption that we make is that the settlement process is one dimensional, or the consolidation takes place in only one dimension. Strictly speaking, consolidation is a three dimensional phenomenon. Imagine a square or a rectangular or a circular foundation, a rectangular loaded area. When it transfers its stress to the soil, settlement is definitely going to take place, and not only vertically, but due to Poisson's effect there could also be lateral movements, and the problem really is three dimensional. Not only that, we just now saw that it is the movement of water and readjustment of particles which is responsible for consolidation. Now, the movement of water, the flow of water inside the soil need not necessarily be in only one direction, let us say vertical, it could be also moving in the lateral direction. In view of these considerations, the settlement phenomenon or the consolidation phenomenon is a three dimensional phenomenon, but in practice it is seen that for many applications it is sufficient to simplify this problem and consider a one dimensional problem. That is, if this is the soil surface and if this is the load transmitted, then we say that the settlement is only in the downward direction, in the direction of the load, even though water may be moving out this way and this way. Irrespective of movement of water, as long as it is in one plane, in the plane of the paper, and as long as settlement is in the direction of this load, we say that it is one dimensional consolidation. Now, under what circumstances we can say that the movement of water will be in one plane, the direction of movement or the settlement of the foundation is also unidirectional. It is possible to assume these ideal conditions when certain requirements are met with. See here in this slide we have the most general case of compression, which is three dimensional, which can be reduced to one dimensional under certain conditions. To name one of them, when the clay stratum is deeply buried, or when, to name a second reason, the applied load is placed over a large area and horizontal variation is negligible in the soil. That means, there is not much variation in the horizontal direction in the soil, and the applied load is placed over a very large area, so that in the region of loading it is reasonable to assume that all the movement of both water and the footing is in one direction. When the clay stratum is deeply buried, when it is closer to the surface, this may not be valid. So, a clay stratum which is deeply buried and is subjected on the surface to a very large load covering a very large area, then the chances are that the compression takes place in one direction, and the so called one dimensional consolidation could be assumed to be reasonably valid. Now, this considerably simplifies the problem of consolidation, because it is a problem of flow of water in only one direction. Let us see next what is the kind of problem that we face in reality, in real life. If you look at this slide, there will be a compressive layer. This is a compressible layer. Very often this compressible layer need not necessarily be the surface layer. Very frequently this compressible layer may be overlain by a relatively less compressible or incompressible layer, and at the bottom also it may be underlain by either a less or an incompressible layer. For example, it is very common to find clay deposits sandwiched between a sand or a gravel layer and a sand or a rock layer. Remember that clays are sedimentary deposits. They are derivatives of sedimentary rocks. These are formed underwater by layer deposition of material which is transported from elsewhere and brought by water, which acts as a transportation agent. And therefore, at different periods of time, according to the law of flotation, different particles will settle with different velocities. Usually the coarser particles will settle down faster in water, especially when the water is stagnant, and finer particles will continue to float for some time and then settle down gradually over a much longer period of time. It is therefore very common to find that there is a sand or a rock layer, that is coarse grained material, above which there will be a finer grained material. It is possible that after a long gap or a long period of time, once again deposition takes place and we get over this fine grained layer another layer which could be coarse grained. The fine grained layers are the ones which are going to cause problems. They are the ones where the permeability is low and the water flows out gradually, where consolidation results. Whereas, in the coarser grained materials, consolidation is not that serious a problem because the permeability is high. So, by and large in practice we often come across a situation where there is a compressible layer which is usually clay, which is sandwiched between two layers which are relatively more pervious and relatively less compressible. And on such a layer, on the surface we may apply a load. This load could be in the form of a fill, that is, you all know that whenever we want to develop a site for constructing a building, we will level the site first. So, if the site is not level, we will put a fill layer and compact it. We will put a layer of loose fill and compact it and thereby make the ground level, assuming that the original surface is not level. And this fill material also acts as a load effectively, not only the building that is going to come above. So, there could be load due to this leveling material, there could be loads arising due to the buildings, and below them there could be a set of layers. One of them may be a compressible layer. Usually it is sandwiched between other pervious layers, but need not necessarily be always so. In the diagram which I have shown here, I have shown only the compressible layer. That is, I have assumed that some load has been transferred up to the sand layer, and now I am only considering the load that has been transferred to the compressible top of the compressible layer. Suppose the compressible layer is subjected to a uniform intensity of loading Q over a very large area, so that its compression can be considered to be one dimensional. Now, what does this mean? Let us again go back to our three phase diagram. Effectively, two phases, solids and voids. Voids are filled with water. The solids have a height h s, the voids have a height h v 1 to begin with. At time instant 1, we have h s and h v 1 as the heights of the soil skeleton, solids and voids, we are assuming unit area. So, if I consider a column of soil with unit base area, then the height virtually represents the volume and the solids have a height H s and the voids have a height H V 1, let us say, to begin with. Now, the load Q is acting on this. As the load Q acts, the consolidation phenomenon starts taking place. Solids are incompressible, only the voids are compressible, and they are compressible in the sense that since water is not compressible, it has to flow out and then the voids will shrink. Now, water flows out gradually and the voids decrease gradually, leading to a slightly compressed skeleton at a time instant 2. So, let us take a look at the next diagram drawn side by side. We have against the solids. Note here that H s remains the same, height of solids remains the same, indicating that the solids are incompressible, whereas the voids H V 1 height H V 1 has now reduced by an amount S and taken a new value H V 2. It is this decrease in height which is known as settlement, and it is this settlement which we are interested in computing. We want to compute the settlement in advance, so that the building can be so designed as to adjust depending upon the amount of settlement that is anticipated. Therefore, this value of S, which is the resulting decrease in height of the voids due to a given building, is what is to be determined or computed. How do we do this? Let us see how this change in voids takes place. Take the first diagram once again. Now, I am calling solids as H s as before. I am calling the initial state of the voids as H V 0, 0th state. The red line here in the first diagram represents the subdivision within the voids, that is water and air. Water particles are incompressible. So, it is only the air which undergoes compression. The only other way to compress is water flowing out, and let us say as the load increases from 0, that is no load, to an equivalent stress value of sigma 1 dash, then solid remaining constant, the voids decrease to a new height H V 1, there is a decrease of delta H 1 and the new void ratio is E 1. Now, suppose the stress is further increased from sigma 1 dash to sigma 2 dash, solids still remain the same, the height still remains the same H s, the voids further decrease to a value H V 2, or there is a settlement equal to delta H 2 and the new void ratio is E 2. So, now we find that as the stress goes on increasing, there is a reduction in height, there is a reduction in void ratio, and it is this void ratio and the resulting decrease in height which we are interested in knowing. Change in void ratio is what we want to know. In the field, it is difficult to determine the change in void ratio. There are no convenient methods to determine the void ratio under an applied load as it goes on changing. So, what we resort to in practice is to take a small specimen, a sample of the soil, make a specimen out of it in the laboratory and test it under load. The equipment that is used for testing a sample in the laboratory is known as the odometer. Odometer is used for simulating the effect of an applied load on a clay layer and study the decrease in thickness of the clay layer and decrease in void ratio of the clay layer, so that we can see how much settlement will take place or how much void ratio reduction will take place under a certain known change in the applied stress. Take this figure. This is a diagrammatic sketch of an odometer or a consolidometer. There is a container within which there is one porous plate and then a sample ring. This white one is a ring in the annular space inside the ring there is a ring like specimen, a cylindrical specimen of known height, usually 25 mm is kept, and above that again there is another porous stone, and the whole thing is kept in water. This entire container is later on filled with water. We can immediately connect this with what we saw in the previous diagram as representative of practical situation. The soil specimen here is bounded on both sides by relatively pervious materials, a porous stone at the top, a porous stone at the bottom. So, this simulates a compressible clay layer sandwiched between two relatively less compressible or porous layers. And further, we have an arrangement for applying a load and to measure with the help of a dial gauge the decrease in height of the soil specimen. So, the components here are an outer container, an inner ring, soil specimen within the inner ring, then there are porous stones, then a dial gauge and load application. Now, what happens when you apply a load like this to a specimen in an odometer? The void ratio changes. In the odometer test, as the void ratio changes, it is possible to estimate the change in void ratio, because we saw in one of the slides earlier that in practice the decrease in height is due to the decrease in void ratio, and the decrease in height or the settlement is what we are interested in. And if we can find the change in void ratio, we can certainly find the change in the height or the thickness, which is what the settlement is all about. So, take here this combination of diagrams. Once again, at no load, skeleton height is Hs, initial height of voids is Hv0, void ratio is E0. At certain load or at a certain load increment equal to say delta p, as the load changes from 0 to sigma 1 dash, we have solids with same height Hs as before and voids with a new height Hv1. This continues further to E2 as the stress increases to sigma 2 dash, and what we find now is that with every increase in load there is a decrease in void ratio, which means that there is a certain relationship between the decrease in void ratio and the decrease in the thickness of the soil specimen. If we can therefore put a soil specimen inside a consolidometer, apply a load and go on studying the change in thickness, that is delta H, there is a way to know what is the corresponding change in void ratio. How do we do that? See here, the solids and the voids which constitute an initial height of H0 total height, where the solids have a height Hs and voids initially have a height Hv0. Let us now translate these heights into volumes. We know that the base area is unity, we are considering soil columns of unit area. These heights can be straight away translated into volumes. For example, the height H0, the total height of the skeleton, will correspond to a total volume V0. The height Hv0 will correspond to a volume of voids Vv, and the height of solids Hs will correspond to a volume of solids Vs. The area being unity, height multiplied by unity will simply give you the volumes, and the void ratio is E0. Now, we know how void ratio is defined. The fundamental definition of void ratio is E is volume of voids divided by volume of solids. The reason why we defined this, as you probably already know, is when we want to compare different states of compression or reduction in thickness or change in void ratio, if we have a parameter in which the denominator or the basis remains constant, then comparison becomes possible. So, void ratio is defined in terms of volume of voids divided by the constant volume of solids. Solids are incompressible. So, the volume of solids remains same, and this is particularly useful in comparing the degree of compression that a soil has undergone at different periods of time or different states of stress. So, here for example, there is a change in void ratio from E 0 to E 1 when the load increases from 0 to sigma 1 dash, and as the load increases further to sigma 2 dash, then the void ratio decreases to epsilon 2. In every single case, this void ratio can be calculated as the volume of voids here, that is H V 1 or H V 2 divided by H s, the volume of the solids. Both H V 1 and H V 2 are measurable. When you have a soil specimen in the odometer, if this is the odometer, porous plate and the soil specimen, when you apply a load and when you have a dial gauge, it is possible to measure the amount of compression that takes place in the soil specimen, that is its change in thickness. So, delta H, whether it is delta H 1 or delta H 2, depending upon the loading increment, it is possible to determine. So, in fact, in practice a series of loads is applied. The load initially is, let us say, some P 1, it is gradually increased until it reaches a certain high value, which simulates the load that is expected to come on a real soil condition due to a real structure. See, after all, what are we trying to do with the help of this odometer? With the help of this odometer, all that we are trying to do is to simulate a certain field condition. So, in this what we do is, we take an actual soil sample from the field, cut a specimen of known specific dimensions, in this case 75 mm diameter, 75 mm diameter and 25 mm height, and we put this specimen and subject it to load and keep on measuring the change in height. And so, we can go on getting the different values of delta H 1, delta H 2 by measuring H V 1 and H V 2 corresponding to various loads sigma 1 dash, sigma 2 dash, sigma 3 dash and so on, until we reach a value of sigma which corresponds almost equal to, or almost is equal to the stress that is likely to be imposed by the load that is going to come due to a building that is likely to be constructed on that soil. And there are methods of computing stress distribution, as we have already seen, and therefore, what is the load or what is the stress sigma which is going to actually come over the soil at the site due to a proposed or envisaged activity can be easily computed in advance, and that can be used here in the consolidometer as the stress up to which the soil specimen should be loaded. And in each case, we measure the change in thickness. Actually, we measure the new thickness every time after every passage of certain amount of time, and then we compute the change in thickness. Once we know the change in thickness, since height translates as volume when the unit base area is constant, the change in thickness also corresponds to change in volume. So, we can write a small equation of the type I have written here. Take the initial and the second or the final state in the given problem. The final state corresponds to a stress of sigma 2 dash, a total height of H 2 with void height H V 2 and decrease in thickness delta H 2. We can write down the change in volume from state 0 to state 2 as V 2 minus V 0. Actually, V 0 is higher. So, we could have written V 0 upon V 0 minus V 2 and reference it with respect to the original volume V 0. So, that we will know change in volume per unit volume, original volume. So, V 2 minus V 0 by V 0 should correspondingly be equal to the height H V 2 of the voids minus the height H V 0 of the voids in at time 0. Actually, this will be minus and this will also be minus, and therefore, it is as good as subtracting second volume from the first volume, and instead of dividing by V 0, we now divide by H V 0 the original height of the voids. We could as well divide by the total height, but then it is only the volume of voids which is changing. Therefore, it is appropriate to relate the change in height to the original height of the voids only, rather than H s plus H v 0. It is advantageous, or it is more appropriate to relate the change in height to H v 0. Okay. This would mean that the total volume can be expressed in terms of volume of solids plus the void ratio. So, 1 plus E 2 minus 1 plus E 0, the new volume original, divided by the original volume 1 plus E 0. So, now what we have achieved is, we have expressed the change in volume in terms of change in void ratio. So, it is 1 plus E 2 minus 1 plus E 0 divided by 1 plus E 0. Let us proceed further. This means it is equal to delta E upon 1 plus E 0, E 1 minus E 2 or E 2 minus E 0 upon 1 plus E 0, or the change in thickness, which is nothing but the settlement, which I may express as, say, delta S. It is nothing but the change in void ratio divided by the original void ratio multiplied by the original thickness H 0. Okay. So, now further we can generalize this expression as S is equal to change in void ratio by original volume, which is 1 plus E 0, multiplied by the original thickness of the original clay layer. So, S is the total settlement due to any given load increment, delta E is the change in void ratio, E 0 is the initial void ratio, and capital H is the initial thickness of the clay layer. This is how we compute the settlement in terms of the void ratios. Suppose we take one simple example now. A 10 meter thick saturated clay layer sandwiched between two sand layers has an initial void ratio of 0.555, a final void ratio of 0.540, and a load applied equal to 100 kilonewtons per meter square. What will be the corresponding settlement? The corresponding settlement will be change in void ratio divided by the original volume, which is 1 plus E 0, multiplied by 10, that is 0.096 meters or 9.6 centimeters. Now, this total settlement depends on E 0 and E f, and E 0 and E f in turn depend on the stresses sigma 0 and the finally applied stress, and hence in order to proceed further, we now need to establish relationships between sigma and the void ratio E. Once we establish relationship between sigma and the void ratio E, we can have a method by which, knowing the anticipated stress change, we can find out what is the anticipated void ratio change. Once we know the void ratio change, we have already seen how to compute the total settlement. So, the next step shall be to relate the void ratio change with the stress change, so that knowing the anticipated stress change, we can still compute the anticipated settlement. Thank you.